So let me give us first some introduction and motivation first. Last year, CERN, which is essentially responsible for the Higgs boson, the hard particle, organized a machine learning challenge called Higgs ML. And the idea there was, can you improve the accuracy of detection of Higgs boson using machine learning? Now, we were late to participate in that, but it was actually kind of motivated for us to look at different Higgs algorithms. We're just not interested in looking at one algorithm, because when you talk to several users, they want multiple algorithms. Now, what happened was, we also looked at this Nature Communications paper, which essentially uses deep learning mechanism to improve the accuracy of detection in exotic particles, which is essentially high energy physics. So, what we can see is that there is significant evidence of using machine learning in science. Similarly, in bio as well, complex biology, there was a paper in few this time which talks about the applications of machine learning in biology. In addition to that, what I was also interested in doing was, can machine learning help solve my problems? So we are interested in three parts. As somebody who's interested in exascale research, there are three parts that everybody is interested in: performance, power, and reliability. And at least at the end of the talk, at that time, I talked about how we can solve some of the resilience problems using machine learning. So as you can see, starting off talk about speech detection, there are tons of other problems, classification problems, clustering problems, big fat mining problems that actually are applicable to science, non-science domains, which is very interesting. Let's take a look at what is the gating process first. Basically, what it means is knowledge discovered from data. So here I'm showing the 5 steps, depending on who you talk to, you have more or less number of steps. The data is here. Pre-processing three happens at the stage, principal component analysis to reduce the dimensionality, transformations such as fast Fourier transformation to frequency domain, mining/learning, which is what is going to be the topic that I'll talk today, and visualization happens a lot. And you can talk to me offline what the time to talk about how visualization actually helps a lot with respect to multiple science domains and non-science domains. In many cases, this step is repeated several times over till scientists are just happy with the model. Now, what are the typical machine learning tasks? Patrick talked about classification, but lots of people use clustering as the first step to classification in order to use the data that they need to process to understand the model. So, for example, here you can see multiple clusters coded for different terms, and essentially they are used to determine the representative points that would represent the entire data set. Similarly, classification, Patrick talked about deep learning as an example. I have given an example of supported machines, which is actually a very widely used standard. The reason it's so widely used is because it's mathematically very stable. It's been there for more than 20 years. And I tell you that within the lab, there are at least 3 domains who support machines to do modern learning. And these are my instruments besides myself. And then there is regression algorithms, which are essentially doing prediction of what the value is going to be as a function of a particular algorithm. So naturally, there's lots of interest into this. There are lots of applications into this in science and non-science domains, and we are really interested in this field now. This is an infographic from IBM. There are certain beats in machine learning, like big data, so to speak, and there is variety of data which I'm not going to talk about. There is volume of data which is very interesting. So, for example, Sun has more than 100 megabytes of data. Not all of it is labeled, but a lot of it is there. Unfortunately, Sun, you would not believe, has machine learning tool called Root, not the best choice of words, which is pretty much. So you have a huge amount of data, but essentially have very small sigma sort of machine learning toolkit which they can use for analysis. Similarly, there is a project called atmospheric radiation measurement. This project has been in hand for almost 20 years, and it's expected to continue for at least another 10 years. The idea there is you get samples from all over the place with sensors which are geographically distributed, and you want to understand the phenomena of clouds, the aerosols that exist in space. So one machine learning task over there, sometimes what happens is, let's say that you have a sensor over here, a plane goes by, all the data that arrives right from the sensor to us is garbage. So machine learning task over there is, can you say, we don't know whether a flow plane flew by, what happened, but we want to essentially classify that data as garbage or not garbage. Something as simple as that. Besides, they would use regression algorithms as well in order to predict the values as well as system. So if I have time to talk about velocity of data, because we have done some work in terms of parallelism with respect to implementing machine learning algorithms, but I'll first start with the one. First, let me give you what is the space in terms of distributed machine learning languages. So, two of them are really popular. One is Spark and MLlib, which is essentially for microeconomics and working. Um, very well widely used in cloud computing space, but the problem here is it's not an native implementation and it doesn't use high performance networks. It uses the TCP/IP, which is not effective for large scale systems. Similarly, Apache Mahout has those restrictions. Now, there are certain other libraries that have come across. Berkeley has Cafe, which is essentially limited to mostly single GPUs or single core systems. NVIDIA has Digits, which was recently released. Torch is another library which is supported by a vendor, a set of community from Facebook, Google, and so on. But the problem really is, with an exception of the work that Patrick presented today, most of this work is actually restricted to single node systems. So you have entirely two ends of the spectrum. One is distributed learning, but they don't use hardware effectively. The other one is single node systems. What we want to build is design a set of algorithms that people use day in, day out, using the best node software. So we know, having been in this HPC space, that if you were to write something in C++ or C, most likely you want to get native performance, with some exceptions. And if you were to use MPI, you will get best performance. And because MPI is so new on different systems, as like the MVAPICH and other MPIs that exist in other on the connects, it provides very good performance. The question becomes is, what are the benefits of designing native compute algorithms? So I can answer this question right here. When I started doing this work and I wrote the first native algorithm, it beat these two libraries so much that it was not even worth putting down. So essentially because these have problems with respect to disk space, not being able to use the network properly and so on. The second one is more interesting for the community over here. What is the whole interconnection MPI machine learning? Is it just a tool computing problem? Probably not. I'll try to answer this question. So what we did first is to essentially for the users build a library called machine learning toolkit for extreme scale. The idea there is we don't want you to know or understand what extreme scale is about. We want us to give you a set of library or interfaces that you can use to learn the model. So for example, we can give you Python bindings, we can give you all sorts of bindings. You run our algorithm. Don't worry about what goes into the back end of this. So what we did was we built 5 algorithms, and these are 5 of the top 10 algorithms that we use in machine learning. Something as simple as k-means, spectral clustering, which is actually very high accuracy clustering algorithm, especially for non-linear data, supported for machines, which is so widely used in so many domains applied over the last 15, 20 years. K-means neighbors, and frequent pattern mining, which is used for finding correlations, of finding frequently occurring things together in space. The idea really there was we want to gear towards supercomputers. And because MPI is also starting to appear on the cloud computing systems, it can actually run for them as well. One of the things that we also did for velocities to support parallel implemented software machines, if I do get time today, I'll talk about that, otherwise we can talk about it offline. We have a version that is released that is being used internally by external folks as well, and the current version is 0.2 alpha. So for those of you who have used supported machines, you would know that there is a de facto library called libsn. But libsn is actually sequential. So one step that we did first for a baseline performance is to make enhanced libsn to use spoken. And we want to include that because as the first step you get performance benefits if you only have single node. If you only have a desktop, you will still get significant performance speed. Okay, and you can go to this website and download this. Alright, so let's get back to the use case. So this is the picture that was released by CERN in 2012 when I found God particle. And what we wanted to see was how good does variance scale does on one particular data set. So what we did was we wanted to learn the model on the UCLA exposure data. So CERN doesn't really release its data set so effectively. So University of California might actually release that that mimics that this sort of data set. It only has 11 billion samples. So let me tell you what it does over here. So this data set has 11 billion samples, and somebody has done the hard work saying which sample is signal. That means it is Higgs boson particle, or which sample is not. And we want to essentially run superconducting machines and be able to learn the model. So that if somebody gives me a new sample that is being generated through my physics, I can say it has Higgs boson, no, it doesn't have Higgs boson. And by the way, loss of accuracy by improving time is not acceptable. The reason is if you go from 80% accuracy to 85% accuracy, you get glitch accuracy. That's what we scan today. Okay. So we used our best supported machine is the default one, which is MPI, and we use an MPI-two here. Uses the most popular supported machine out there, 170. It's I think the original table is published like 15, 20,000 times. I don't remember. There's JC times are from 1999 or 2000. Okay, so let me tell you what happened there. We wanted to, when I started thinking, I thought this will actually run an hour or so. We used 6,000 codes with Intel has learned InfiniBand and MVAPICH2 for 2 days. Basically, it essentially reserved the entire system. We have a system called KNL constants. We reserved the entire system and we could only complete 2 experiments. It took such a long time to actually run this on 6,000 codes. The objective really was, can we improve our accuracy in comparison to function? But learn from this, what I learned was first we should reduce execution time. And obviously we are not, it is reducing accuracy at the cost of execution time is not reducible. So one thing that we learned is also probably need larger scale access. So we went after that. So I applied for this Argos directors, especially I wanted to receive 2 million quotas from them and initial results encouraging. But bottom line is our primary execution is still KNL constants and MVAPICH2 and MPI-one. So let's go back to this algorithm. What can we do about it? So let's consider a very simplistic case. So here there are 2 types of points. There are blue points and there are pink points. But there are 2 types of points, and essentially there is a classifier which is the set of points that distinct blue points from red points. Basically, this is a very small microcosm of what machine learning in classification is all about. So what you would typically do is you would have a non-linear classifier that actually goes to the range. So observation number 1. In the entire data set, only a small fraction of samples define the boundary. Those samples that are actually encircled over here are noise correlates. They are the ones that distinguish one sample of one type to some sample of another. Observation number 2. There is a sequential algorithm that essentially adaptively eliminates those worthless samples, but there is no pattern algorithm. So this work was published by Jokins in Club 5, but there is no pattern algorithm. Not economic distributed, not even shared forget distributed. Third, there is reducing accuracy at cost of time improvement is not required. Nobody will take that. If you cannot reproduce the results in a deterministic way, just like patterns. If I tell you this time the accuracy is going to be 82%, next time it's going to be 86%, nobody will take it. Most of the scientists will say next time it's going to be 60%. So recently there was work published by Berkeley in anti-defense investigative award, which essentially has an approach called communication avoiding estimation, but it reduces the accuracy. It actually does very well in terms of time, but it can reduce accuracy 4, 6, 10%. So something like that is not good. Okay, so we did this. We wouldn't go into the math around this. I'll talk about the communication aspect in the next slide. But what we did was we essentially took this 2 data sets. We actually published this paper recently in Cluster, but this is just 2 data sets out of the 10 data sets that we evaluated our approach on and showed the benefit. And all of this uses advantage. And the constants machine and also the PNL and cascade machine. supercomputer in the standard. So here you can see this 64 nodes and 120 nodes to 56 nodes. LibSTM, this is LibSTM did not even compete in the LibSTM open enhanced by ourselves, which actually improved the execution time, did not actually compete in 2 years. And you are really disappointed by that because if you have more than 5,000 samples, it takes a long time to actually do that. On the other hand, this is our default algorithm, which does the issue. This is the most optimized algorithm we have. So we have some heuristics to adapt to the samples. We can actually improve the execution time by 2x on 24 processes. And it has 2 strong scales, and you can imagine the work per process decreases, but the benefits still exist. This is another interesting piece of data set from cybersecurity. Here is the task. Given a URL, you have to classify whether it is authentic or not. And this is a pretty complicated data set to actually classify. So here if you see improvement on 256 nodes, we get almost 250x improvement in comparison to the data set. So this is probably, at least from what I've seen so far, one of the largest evaluations supported machines with this new algorithm. I'm not seeing this algorithm installed in the algorithm, and obviously we did evaluation with MPI-two. We also did evaluation with other MPIs and performance of ones, not even those. We did an evaluation with MLDM and the performance with respect to typically with respect to automation was not so good. So, okay. So now let's just talk about some real interesting stuff. Okay. So let me go into only that much depth of the algorithm as it would not be dry for us. Okay. So what does the algorithm do at very high level? So obviously it's a convergence algorithm, like the radius algorithm that's Patrick talked about. It does 3 steps in the broad space. So what it first does is it picks up 2 samples in its entire data set, which it thinks are the best ones to go to the class, to go to the minimum loss function. And this is the context optimization problem. So what it does is first it picks up 2 samples, and each sample has those 2 data sets because it distributes this data set on multiple processes. Each process who owns that sample has to do a criteria to everybody else. So there are potentially 2 NGL broadcasts that are going on at the same time. Now what is the time complexity of that? L plus NG, which is from the logic model, L is the latency, and the message size, inverse NG is the bandwidth. Log GP is the expected execution time for that step itself. It could be more depending on how the broadcast actually is designed. What is happening here? So this is the computational part of it. So let's say there are n samples, p processes, and because you have 2 samples for which you have to do this calculation, you multiply by 2. And there is this curve calculation which is going back, but it's called Gaussian curve, and you calculate that curve for each pair of steps to pair of samples is close to 190. Okay, so it takes this much amount of time to actually do this calculation. And then finally, you do a multitasking to figure out what these values are going to be, but it's only 2 scales, so I'm knowing the message size and inverse bandwidth. So it's only L not log G. So log P. Okay, now let me explain this stuff, right? So on the y-axis, on the x-axis, we have the number of iterations. On the y-axis, we have the number of samples that are still active in supercomputer machines. So this green algorithm is the default algorithm. So obviously for this kind of algorithm, the time complexity is n divided by p multiplied by 2 multiplied by 2 plus L plus ng dot log p. I'm ignoring this term because typically message size could range from few bytes to few kilobytes to megabyte depending on the mesh tag. Right? So this is good. So what you can do over here is you can arbitrarily increase your problem size and reduce the time it takes to spend in computation. Now let's look at this solution. Okay? For very good for the purpose of this talk, you can see that this is kind of an exponential area. So what is happening is at this step or at a few steps, I'm decreasing the sample that are likely actually contribute to this model generation. So what is happening over here? Now you multiply this with this exponential decay function. As you decrease over here, let's look at over here. The total time for computation is decreasing, but the total time for communication is increasing. So Amber's law starts to kick in after this point. And that's actually the reason why strong state of this application does not work very effectively. Now the question is that actually I want, and I hope Gilad is here, is shrinking algorithm. That's what I thought is. Shrinking algorithm converts a compute intensive problem into a communication intensive problem. Just look at the number of iterations. Oops. Just look at the number of iterations it takes after this. It's still a huge number of iterations before it actually goes to the rules. And because the algorithm is precise, at some point you have to bring back on samples and then the shrinking continue again. But it still requires a lot of improvement in terms of execution. So what we generally think is that machine learning may or may not be communication intensive, but here with this back of the envelope calculation, we prove this problem actually is communication intensive. So for some space like between here and here, it had a very good broadcast algorithm, it had a very good monitoring algorithm. If you have properties like hard-to-place algorithms, higher bandwidth, low latency, that could make a huge difference on modern broadcast. That you can again tune and repeat, but frankly speaking, there's not much you can do with it. But that's what we have. Okay. So I didn't really plan to go into a lot of details with this. So what is really happening is most of the use cases are actually high loss. Up to now I talked about high volume use cases, but in reality what is happening is you're seeing the data from sensors on your face, even in science domains or non-science domains, at an unprecedented rate. Yet, there are no algorithms in parallel that actually learn this model, essentially having used any chemical sort of that. So our first step to solve this problem of velocity. So for example, some here produces almost 20 gigabit per second. I don't know how much of that data is actually used. I mean, there are some questions of how much they keep, how much they discard, but that's the number they have. ARM again produces a terabyte a day, which is not tremendously problematic, but we just start to run a complicated algorithm on it, like sample techniques, which I won't talk about today, it becomes problematic. So what we did was, we built this incremental sort of a parallel algorithm, where we did, what we do is we receive this weight of samples in weight 0, we learn the model, okay? Now, our model can be used for testing as well, but these models, we essentially save these support vectors, and then we combine with the samples in the next window or existing support vectors and learn the models. So over a period of time, we are able to converge on a very accurate model in comparison to essentially similar to what sequential algorithms is. Obviously, sequential algorithms do not tie to time velocity, so they can only do that much. We did this with Scikit, and we are getting used MPI-2 for this. And the problem with that software is that it's very popular, but non-implemented and it's sequential. So this is again something that we have not released yet, but my target is that by supercomputing time frame, when we have hard rate, we can actually release. This is just an infographic to show how parallelism happens, and I'm abstracting the details as to how the models get combined most of the Okay? Alright. Now let's show something cool, right? So something solving my own problem, right? We want to solve a problem in the database. So everybody talks about software learns, hardware learns. So let me give some, let me redefine terminology, right? A fault does not imply an error. An error is when the application is in a state that it cannot continue to function properly. But a fault may or may not be working, right? So let's say that, and what architecture does is, if there is a single bit flip, permanent or transient or intermittent, it will automatically detect and correct it. The problem is when you have a double bit fault in memory, it can be detected but it cannot be corrected, right? Now the question lies to us is the probability of a double bit fault happening is low. The intuitively the probability that that WMA fault will actually cause error in an application is even low. But we don't, right? So what we really want to do over here is to essentially do something like fault modeling. Given this WMA fault, will it result in an application error or not? That's the objective, right? So this essentially infographic shows what happens on critical systems, which essentially has an thing called enhanced machine check architecture, which can actually tell you that a double fault happened or a double fault happened. And lots of published papers in SC12, SC13 on these things. And what we want to do is our fault model to say, using some well-known training data, whether it is not going to be resulting in an error or whether it is going to be resulting in an error. So what we do is I'm not going to go into the details of the pipeline that we have built in order to generate this data set, because really the key is how do you generate this data set and what are the features that describe the model. And that's always a very non-linear process. But I go from point to point, which is what we find interesting. So with a model, so this is for 3 different applications. So first of all, we want to understand how resilient is support recognition itself for models. How resilient is not a scam, which is an application of interest and foundation chemistry application to models. And the third one is Ludesh, which is for the unstructured mesh hydrodynamics from the room. So we took these 3 applications and we did a bunch of things with respect to what are the features, application independent features, application dependent features, where should we insert the fault, we have a class imbalance problem, how we solve that. All you have to report is this number. This number is the accuracy. What this shows is, given a double-rate fault in that system, will it classify with high accuracy when it's a fault, whether it's an error or not? And with all that, we are getting close to 98, 99%, and 100%. So what it means is, defining an error as an error is very important. But if you define something that is not an error as an error, sometimes that's okay. So with this, all the things, all the faults that errors are classified as rating, but some things that are non-error are classified with an accuracy of 60 to 70 degrees, depending on that. But that's a still very solid number, because if you can say read the execution of an application 60 to 80% of the time, that's a huge benefit to that work. Okay, so I don't know how much time I have, probably 3-4 minutes. We are very interested in looking at deep learning as well. This is something that I have not looked at mostly because I'm looking at MLDM's work in this ICML, prediction and machine learning, and finally we talked about this belief that extinct GT that exists in that area. But we have a statistic that we came this summer and talked about, can we improve the execution time of deep neural nets, deep belief nets, and convolutional neural networks without loss of. So we have not published results. I'm not going to talk in detail, but the results are very encouraging. So hopefully we'll get published soon. We'll talk about that. Obviously, I'm from the HPC space, so I'm looking at fault on machine learning algorithms. And I want to build algorithms, not the traditional ones which you checkpoint based on. I want to build algorithms that essentially have very low space complexity, very low time complexity, potentially not going to checkpoint. So again, we build fault on support machines, which essentially does no checkpointing, guarantees accuracy, and just have this for recovery. This is again still a little bit on the backdrop because we have to understand what we can provide as new. There's not enough in this space at Mind Research, at media, other places. What the last question, because we are actually performance modeling group in many ways. We have mostly done performance modeling using analytical sort of modeling. We are interested in this overarching question: can modeling and machine learning provide new insights? And why should we do modeling and machine learning? Machine learning is not just something that we want to do for fun. Machine learning becomes very interesting when parameters which are used to train the model have non-linear effects. So think about this. When I'm building the performance of an application, level cache size, big users, we are all that stuff. I know that they are not independent of each other, so I cannot do an analytical model. That's the machine learning approach. And this is something that a few of my colleagues are actually working on, how to collect this data, how to learn these algorithms and so on. Okay, enough said. Thank you for giving me the opportunity to talk here, and I'll be happy to take any questions. Yes, thank you.
Any questions for Abhinav?
Do you have any results of comparing your MaTex with MLDM and Mahout?
With what, sorry?
MLDM and Mahout.
I don't have those results here, but they, especially Mahout's performance was pretty bad because Hadoop essentially uses file I or not, and even for something as simple as multiple iterations, it would do multiple IOs. Spark MLlib has another problem that it doesn't have non-linear supported function handling. It only has linear estimate, and we more interested in non-linear estimate. So that's again the reason. Besides not using InfiniBand or any other sort of time forms. So I don't really have results over here, but I can probably necessarily get.
Okay.
Any other question? Okay, otherwise, let's again thank Abhinav and we will switch to the next talk. So interestingly, from machine learning to fault tolerance, now we'll move to checkpoint restart. Okay? So I didn't know that when I was scheduling this talk, it will lead to start with machine learning, fault tolerance, and then checkpoint restart. So it will be given by Professor Gene Cooperman. And Professor Cooperman works in the high performance computing and scalable applications for computational algebra. He received his PhD from Brown University in '78 and spent 6 years in basic research at GT laboratories before coming to Northeastern University in 1986. So since then, he has been a full professor since 1992. In 2014, he was awarded a 5-year IDX chair of attractivity at the University of Toulouse, capital A, in France. Since 2004, he has led the DMTCP project. Many of you might be familiar. It's the distributed multi-threaded checkpointing support. So that software has been downloaded more than 9,000 times. He also has a 15-year relationship with CERN, where his work on semi-automatic thread parallelization of task-oriented software is included in the million-line Giant4 high-energy physics simulator. So his current research questions include the limits of transparent checkpoint restart for supercomputing, engineering desktops, virtual machines, GPU-accelerated graphics, cloud management, and big data. So his talk will be titled today, Transparent Checkpoint Restart, Rethinking the HPC MR. So let's welcome Professor Cooper.